In section 5.1, we look at number theory of prime and composite numbers. So number theory is primarily concerned with the properties of numbers used for counting, namely 1, 2, 3, 4, 5, and so on. The set of counting numbers is also called the set of natural numbers. So these are the numbers we learned first as a kid, starting with 1, and it keeps increasing. Any natural number can be expressed as the product of two or more natural numbers. The natural numbers that are multiplied are called the factors of the product. In general, let A and B represent natural numbers. We say that A is divisible by B if the operation of dividing A by B leaves a remainder of 0. A natural number is divisible by all of its factors. So if A and B are natural numbers, A is divisible by B if the operation of dividing A by B leaves a remainder of 0. This is the same as saying that B is a divisor of A or B divides A. All three statements are symbolized by writing B vertical bar A. So for example, we would write 12 vertical bar 24 because 12 divides 24, or 24 divided by 12 leaves a remainder of 0. Thus, 24 is divisible by 12. However, if we write 13 vertical bar 24, this means 13 divides 24, or 24 divided by 13 leaves a remainder of 0, but this is not true. So we just put a line through the vertical bar to indicate that it does not divide evenly. And so we have some rules for divisibility. For a number to be divisible by 2, the last digit is 0, 2, 4, 6, or 8. So it's an even number. So 5,892,796 is divisible by 2 because that last digit is 6. To be divisible by 3, the sum of the digits must be divisible by 3. So 52,341 is divisible by 3 because when I add 5, 2, 3, 4, and 1 together, I get 15, and 15 is divisible by 3. To be divisible by 4, the last two digits form a number divisible by 4. So 3,947,136 is divisible by 4 because 36 is divisible by 4. To be divisible by 5, the number ends in a 0 or a 5. For a number to be divisible by 6, the number is divisible by both 2 and 3. In other words, the number is even and the sum of its digits is divisible by 3. To be divisible by 8, the last three digits form a number that is divisible by 8. So 593,777,832 is divisible by 8 because 832 is divisible by 8. To be divisible by 9, the sum of the digits must be divisible by 9. To be divisible by 10, the last digit must be 0. And to be divisible by 12, the number is divisible by both 3 and 4. In other words, the sum of the digits is divisible by 3, and the last two digits form a number divisible by 4. You do not need to memorize this entire table because you have a calculator that can do the work for you. So which of the following statements is true? Is 4 divisible? We have 3,754,086. So looking back at the table, for a number to be divisible by 4, that means that the last two digits form a number divisible by 4. So because our last two numbers are 86, can I take 86 divided by 4? And since 86 is not divisible by 4, this means that this is a false statement. What about the second one? We've got 9 is not divisible, and we've got 4,119,706,413. And so by the table, it says that the sum of the digits must be divisible by 9. So we need to add them together. 4 plus 1 plus 1 plus 9 plus 7 plus 0 plus 6 plus 4 plus 1 plus 3, which gives me 36. And is 36 divisible by 9? It is. You would get 4. And since this is divisible, that means that the entire thing has to be divisible. So because we have that bar inside my vertical line, this is now a false statement because it is divisible. What about 8 into 677,840? What this one says back in the table is that the last 3 digits need to form a number that is divisible by 8. So we're looking at 840, and we want to see if that is divisible by 8. And it is, and we get 105. And since this is divisible, that means that this is a true statement. Now let's talk about prime factorization. A prime number is a natural number greater than 1 that has only itself and 1 as factors. So using this definition, we see that the number 7 is a prime number because it only has 1 and 7 as factors. Said in another way, 7 is prime because it is divisible by only 1 and itself 7. The first 10 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Each number in this list has exactly 2 divisors, itself and 1. So a composite number is a natural number greater than 1 that is divisible by a number other than itself and 1. So you're either prime or you're composite. Using this definition, the first 10 composite numbers are 4, 6, 8, 9, 10, 12, 14, 15, 16, and 18. Each number in this list has at least 3 distinct divisors. By the definitions above, both prime numbers and composite numbers must be natural numbers greater than 1. So the natural number 1 is neither prime nor composite. Every composite number can be expressed as a product of prime numbers. Expressing a composite number as a product of prime numbers is called a prime factorization. There is only one factorization possible for any given composite number. So the fundamental theorem of arithmetic says that every composite number can be expressed as a product of prime numbers in one and only one way. The order of the factors is disregarded. One method used to find the prime factorization of a composite number is called a factor tree. To use this method, begin by selecting any 2 numbers other than 1 whose product is the number to be factored. 1 or both of the factors may not be prime numbers. You continue to factor composite numbers and stop when all the numbers are prime. So let's look at 700. So we want to list 700 up at the top. And we need to find 2 factors of 700. It doesn't matter what 2 you pick, because once we're done, we're going to get the exact same prime numbers. So I am going to pick 7 and 100. Well, 7 is prime, so we're going to leave that end alone, but 100 could be broken down further. I'm going to pick 2 and 50. Well, 2 is prime, But 50 can be broken down even further. Well, 50 can be broken down into 2 and 25. Again, 2 is prime, and 25 can be broken down one last time, and we get 5 and 5, which both of those are prime. So just compiling all this together, 700 is equal to 7 times 2 times 2 times 5 times 5. But we can simplify this with our exponents. And so this is 7 times 2 squared times 5 squared. A lot of times we will write this in increasing order. So we would just write 2 squared times 5 squared times 7. Let's find the prime factorization of 120. So again, it doesn't matter which ones you pick because once you're done, you're going to get the same answer. So I'm going to pick 12 and 10. Well, 10 can be broken down into 2 and 5. And those are both prime numbers. And 12 can be broken down into 3 and 4. 3 is prime, but 4 is not, so we just need to break that down one more time. And we get 2 and 2, which are both prime. So 120 is 2 times 5 times 3 times 2 times 2. Or this is 2 cubed times 3 times 5. The greatest common divisor of 2 or more natural numbers is the largest number that is a divisor or factor of all the numbers. For example, 8 is the greatest common divisor of 32 and 40 because it is the largest natural number that divides both 32 and 40. Some pairs of numbers have 1 as their greatest common divisor. Such number pairs are said to be relatively prime. So for example, the greatest common divisor of 5 and 26 is 1. So these are relatively prime. The greatest common divisor can be found using prime factorizations. So to find the greatest common divisor of 2 or more numbers, you're going to write the prime factorization of each number. You'll select each prime factor with the smallest exponent that is common to each of the prime factorizations, and then form the product of the numbers from step 2, and the greatest common divisor is the product of these factors. So let's find the greatest common divisor of 216 and 234. Let's look at 216 first. So 216 can be broken apart as 2 and 108. We got 2 that's prime. 108 can be broken down. That's 2 and 54. And 54 can be broken down. Which is 2 and 27. 27 can be broken down into 3 and 9. And 9 can be broken down into 3 and 3. And so the prime factorization of 216 is 2 times 2 times 2. Times 3 times 3 times 3. Or we can write this as 2 cubed times 3 cubed. We want to do the same thing for 234. So 234 can be broken apart as 2 and 117. 117 can be broken apart as 3 and 39. And 39 can be broken apart as 3 and 13. And so 234 is 2 times 3 times 3 times 13, or 2 times 3 squared times 13. Now we want to see which ones are common to both. So looking at my 2 factorizations, we have 2 that's common, and we have 3 that's common. We want to make sure that we pick the smallest exponent that's present. So out of the 2's, the exponent is going to be 2 to the first, because it's the smaller of the 2. And out of the 3's, we're going to use the 3 squared. And so we end up getting 2 times 9, which is 18. And that's going to be your greatest common divisor. Let's go ahead and try another one. And so we want to do the same process with 225 and 825. $2.25 can be broken down as 5 and 45. 45 can be broken down as 5 and 9. And 9 can be broken down as 3 and 3. And so 225 is 5 times 5 times 3 times 3. Or we have 3 squared times 5 squared. Let's go ahead and do the same thing for 825. 825 can be broken down as 5 and 165. 165 can be broken down as 5 and 33. And 33 can be broken down as 3 and 11. So 825 is 5 times 5 times 3 times 11, or we can write this as 3 times 5 squared times 11. And so we want to see what they have in common. They have a 3 in common, and they have a 5 in common. And then we take the lowest power. So out of the 3's, we're going to take 3 to the first. And out of the 5's, they have the same power, so it doesn't really matter. So we get 3 times 25, which is 75. And that's your greatest common divisor. So for an intramural league, you need to divide 40 men and 24 women into all male and all female teams so that each team has the same number of people. What is the largest number of people that can be placed on a team? This is just a word problem to figure out what the greatest common divisor is between 40 and 24. So we need to break apart 40. That's 4 and 10. And 4 is 2 and 2. and 10 is 2 and 5. So 40 is 2 times 2 times 2 times 5, or we get 2 cubed times 5. And we want to do the same thing for 24. 24 is 4 and 6. But 4 is 2 and 2, and 6 is 2 and 3. So we get 2 times 2 times 2 times 3. Or that's 2 cubed times 3. And so what they have in common is they both have 2, and they're actually both raised to the same power. So 2 cubed, which is 8, and that's going to be your greatest common divisor. So that we can place 8 people on each team. Now, the least common multiple of 2 or more natural numbers is the smallest natural number that is divisible by all of the numbers. So we're going to write the prime factorization for each number. You're going to select every prime factor that occurs, raise to the greatest power to which it occurs in these factorizations, and then you're going to form the product of the numbers from step 2. So they start off the same, but they end a little bit different. So let's go ahead and find the least common multiple of 144 and 300. (144) is 12 and 12. Well, 12 is 3 and 4. Our 3's are prime, but we can break down 4 into 2 and 2. And so 144 is 3 times 2 times 2 times 3 times 2 times 2. Or we can write this as 2 to the 4th times 3 squared. Let's do the same thing with 300. That's 3 and 100. 100 can be broken down into 10 and 10. And both of these can be broken down into 2 and 5. And so 300 is 3 times 2 times 5 times 2 times 5. Or we can write this as 2 squared times 3 times 5 squared. So what we do for the least common multiple is we want to make sure that every number is present. So I'm going to have 2, I'm going to have 3, and then coming over to the other one, I already have 2, so we only need to write it once. I already have 3, but I need the new one of 5. And we want to make sure we take the highest power that's present. So for the 2's, I'm going to bring 2 to the 4th over. For the 3's, I'm going to bring 3 squared over. And for the 5's, I only have one choice, which is 5 squared. Well, 2 to the 4th is 16. 3 squared is 9, and 5 squared is 25. And when I multiply that all together, I end up with 3,600, and that's my least common multiple. So for greatest common divisor, you only took what was common to both and the smallest exponent. For least common multiple, you take all of the factors and raise it to the highest power that's present. So let's go ahead and try this for 18 and 30 as well. 18 is 2 and 9. And 9 is 3 and 3. So 18 is 2 times 3 times 3, or 2 times 3 squared. Let's go ahead and do 30. 30 is 3 and 10. And 10 is 2 and 5. So we have 3 times 2 times 5. And I'm just going to write this in increasing order. And so let's go ahead and make sure we get all of the numbers. We have 2 and 3. And then in the next one we have 2 and 3 again. But we also have 5. So out of the 2's, we're going to take just 2 because they're both raised to the first power. Out of 3, we're going to take 3 squared. And for 5, we only have one choice, which is 5. So we have 2 times 9 times 5. And when I multiply this all together, I end up with 90. And example number 9. A movie theater runs its films continuously. One movie runs for 80 minutes and a second runs for 120 minutes. Both movies begin at 4 p.m. When will the movies begin again at the same time? So this is a least common multiple problem. So we want to break down 80 and 120. So 80 is 2 and 40. 40 can be 4 and 10. 4 is 2 and 2, and 10 is 2 and 5. And so this is 2 times 2 times 2 times 2 times 5. Or we can write this as 2 to the 4th times 5. Let's do 120 minutes as well. 120 is 2 and 60. And 60 can be broken down as 6 and 10. 6 is 2 and 3, and 10 is 2 and 5. And so 120 is 2 times 2 times 3 times 2 times 5, or this is just 2 cubed times 3 times 5. And so we want the LCM. We have our 2 and our 5. We've got 2. The 3 is new, so we need to include it. And then we've got 5 again. So taking the highest power that's present, for 2, that's going to be 2 to the 4th. For 5s, it's just going to be 5 to the 1st. And the same thing for 3. 2 to the 4th is 16 times 5 times 3, which gives me 240. This is the minutes. And so that's about 4 hours. So if my movies started at 4 p.m., in the next 4 hours at 8 p.m. is when they're going to start at the exact same time again.